session today. And today we have a talk of Viktor Yuskovych on asymptotics of solutions of SDE with jumps. Please.
Good afternoon. My name is Viktor Yuskovych, and I am a PhD student at Kyiv Polytechnic Institute. In my talk today, I will present my recent results on asymptotics of solutions of stochastic differential equations with jumps. This topic is a little more general than the announced one, asymptotic behavior of solutions of SDEs with Lévy noise. But I will present results for Lévy noise as well. The first who started studying the asymptotic behavior of solutions of stochastic differential equations were Gichman and Skorokhod in 1968. In their book, they considered solutions of autonomous stochastic differential equations and developed methods to determine their asymptotic behavior, namely transience and recurrence as time goes to infinity. Also, they studied the exact asymptotics of these solutions. Later, Keller, Kirsten, and Rossler studied similar problems. Samoilenko, Stanzhitsky, Novak studied the asymptotic equivalence of solutions of systems of weakly nonlinear SDEs and ODEs. Buldygin, Indlekhofer, Klesov, Steinebach, Timoshenko studied asymptotic equivalence of solutions of non-autonomous SDEs and ODEs. Pavlyukiewicz, Pilipenko, and Proske studied the selection problem for stochastic differential equations with small self-similar noise. In my previous study, I considered multidimensional SDEs and studied transience, angle stabilization, and asymptotics for their solutions.
Excuse me, may I have a question?
Yes.
When you say that you study or this mentioned authors studied asymptotics, maybe you mean asymptotic in almost sure sense or what?
Yes.
Because, okay, yeah, thank you. Okay.
Let's start with the main result. Let X be a solution of the following SDE. Notice that besides the drift coefficient A and the diffusion coefficient B, this SDE contains a coefficient C and this term, which I will call the Poisson coefficient and Poisson term. These SDEs I will call SDEs with jumps. Here, W is a Wiener process. The tilde n is a compensated Poisson random measure with an intensity measure nu. Let alpha be from 0 to 1 and A be positive. Consider the following theorem. In my talk today,
Poissonian measure and Wiener process are independent.
Independent, yes. Thank you. In my talk today, I suppose that it is given that the solution is transient. So the first condition is that X goes to plus infinity as time goes to infinity almost surely holds. The second condition says that the drift coefficient A has the following power asymptotics. As well, it is bounded by some power function. The third condition estimates...
I am sorry, which values of alpha are allowed?
From 0 to 1.
From 0 to 1. Thank you.
The third condition estimates the growth rate of the noise. We will see later that the properties of the Wiener noise and this Poisson noise are quite similar. So on the left-hand side, I just summed up these noises and estimated them by some power function. Since I squared B and C, here I squared, I write 2 beta in the right-hand side, so it makes sense. Notice that notice the relationship between alpha and beta. Beta in the third condition should be non-negative and less than 1 plus alpha over 2. Under these three conditions, we can prove that the solution X has the following asymptotics, almost surely. Notice that this asymptotics is non-random, and also it is nothing but the asymptotics of the solution of the following ODE. dx of t equals ax to the power alpha of t, and the starting point let be 1. So this asymptotics is nothing but the asymptotics of the following ODE, of the solution of the following ODE. And now I'm going to give an idea of proof. It would be easier to consider a stochastic differential equation with a linear drift instead of power 1. So let's reduce the problem to the linear case. To do this, we are going to perform an appropriate transformation of the phase space. To do this, we need a generalized ethos lemma for SDs with jumps. Let f be a twice continuously differentiable function. Then the following ethos formula holds. Notice that in the new drift coefficient tilde a, besides these two familiar terms from the classical ethos formula, an additional integral term arises. This term in purple, in violet. Also, there is a new Poisson coefficient tilde c of this form. Later, we will obtain some asymptotical estimates for these violet terms. Also, notice the origin of the violet terms. In this term, under the integral, we have nothing but the remainder of Taylor's formula of order 2. And in this term, we have the remainder of Taylor's formula of order 1. And now apply the generalized ethos lemma to the process f of x, which we denote with tilde x. With a twice continuously differentiable function f, such that it is 0 for negative arguments, and it is the following power function for x greater than 1. Then tilde x has the following stochastic differential. Notice that we have differential of tilde x on the left-hand side, but here, these coefficients tilde b, tilde c, depend on x, on the original process. By applying ethos lemma, we reduce the main problem to the following linear one. Suppose that the following conditions hold. The first condition...
Excuse me, is it necessary to write this xt minus when we have the integral ODT?
No, here it's not necessary, and here it's not necessary, but here it's important.
Yeah, of course, of course. Okay.
So suppose these three conditions hold. The first condition remains the same. The second condition says that the new drift coefficient tilde A is equivalent to A asymptotically and is bounded. The third condition estimates the noise by some power function with exponent beta, which is from 0 to 1/2.
And now beta is another one.
Yes. Now beta is from 0 to 1/2. And now we have a linear yeah, here everywhere should be tildes. Okay.
I'm sorry, I have a question. So you say that F in C2,
Yes.
but alpha is from 0 to 1. So,
Yes.
But X only when X is greater than
okay, I see.
Yes. So this function is 0, then it behaves
I see.
such a way it is twice continuously differentiable, and then it is power function. Okay. Well, so if these three conditions hold, then the transformed solution tilde x, the transformed solution tilde x is asymptotically equivalent to the following linear function, almost surely. Before obtaining some asymptotic estimates, we need to estimate the second moment of tilde x. For this estimate, we will exploit the following generalized Grunwald's inequality. Let V and G be non-negative Cadillac functions and G be non-decreasing. Let C be positive and beta be from 0 to 1. The following generalization of Grunwald's inequality is by Bihari, who generalized it for arbitrary function under the integral, but I stated for a power function, and Vendrov, who generalized for a non-constant term G.
I'm sorry, if you're going for history, I think Lassalle has also this form inequality. So it's sometimes referred Bihari and Lassalle.
Okay. Okay, thank you. I found these references in the book of Mao.
Yeah, it's possible, but still I think it's...
Victor, and there is no G in the right-hand side of the last
I'm
inequality.
sorry.
Yeah.
I decided because H I will use later, so G. Thank you. We can estimate the second moment of tilde x using the generalized Grunwald's inequality and obtain the following quadratic estimate, that the second moment of tilde x is controlled by such quadratic expression. Now I'm going to show the idea of proof. So to obtain this estimate, first we square both left and right hand sides. Then we use the inequality that the square of sum is less than the number of terms, which is 4. I'm sorry, here should not be square, but now when I estimate this square, we have the following expression with the following inequality with coefficient 4, which I write here, 1/4. Then take expectations. Like this. Use the Cauchy-Schwarz inequality for the drift integral so that it is less than or equal to t expectation of integral of a tilde squared. Then use the Ito isometry for these two integrals. Okay, so Ito isometry, and obtain integrals of squares. Okay, maybe I should write specifically. This is less than or equal, this is equal to expectation integral b tilde squared ds. And there is also some Ito isometry for such integrals with respect to a compensated Poisson measure. These integrals are martingales. So it equals to expectation integral c tilde squared nu, the intensity of n du ds. Then remember that the tilde a is bounded. So here we have less than or equal to t squared, and use the condition for noise, estimating the noise. So we have some estimate here, and here we will have some integrals. Also, there we use Jensen inequality, and finally use the general Grunwald's inequality, which implies the quadratic estimate for the second moment of tilde x. And now we are going to obtain some asymptotic estimates for each term in the Ito formula. Let's start with the following important proposition, which allows us to prove the almost sure convergence for stochastic processes. Let f be a stochastic process. If the following series converges, then the process f goes to 0 almost surely. It is easy to prove this result by applying the nth term test for the series. I write f squared here because it is convenient for further applications for martingales. Also notice that this sequence of exponentially growing segments, like 1 to 2, 2 to 4, 4 to 8, and so on, also is important for further applications for martingales. This technique is often used when one studies the asymptotic behavior of martingales. The following proposition will be useful for estimating the drift integral. Let A be a stochastic process and alpha be non-negative. If the second moment of A has the following power asymptotics, then the integral of A has the following power asymptotic estimate almost surely. To prove this, use the previous proposition and exploit Cauchy-Schwarz inequality. The following proposition will be useful for estimating the Wiener integral and the Poisson integral, which are martingales. Let M be a square integrable martingale and mu be a real number. If the second moment of M has the following big O estimate, then the martingale has the following power asymptotic estimate almost surely. To prove this, use the asymptotic estimates for stochastic processes proposition and exploit Dup's martingale inequality. The following proposition is the consequence of the previous one for Wiener integrals. Let B be a stochastic process and beta be non-negative. if the second moment of B has the following power estimate, then the following Wiener integral with integrand B has the following power asymptotic estimate almost surely. To prove this, use the previous proposition and exploit Ito's isometry. By the way, you can easily check that this result is consistent with the known power asymptotics estimates for the Wiener process. Let B be 1 and beta be 0. Then this proposition yields that for any gamma greater than 1, greater than 1/2, right? The Wiener process is O small of t to the power gamma, which is a known fact. The following proposition is the consequence of the previous one, or I'm sorry. We can obtain a similar result for Poisson integrals. Let C be a stochastic process. Of course, everywhere I suppose that it is nicely measurable in order to use to take integrals expectations and use Ito's isometry. And let beta be non-negative. If the second moment of C squared integrated with respect to the measure nu has the following power estimate, then the following Poisson integral with integrand C has the following power asymptotic estimate almost surely. The proof is the same as for the Wiener process, as for the Wiener integrals. Just remember how the Ito isometry looks like for such Poisson integrals. A quite technically challenging step for proving the result is to obtain the following asymptotic estimates for violet terms. Remember, terms in violet in the Ito's formula for SDEs with jumps. The idea of proof is as follows. Consider each integral separately on small values of C and large values of C. For small values, we use Taylor's theorem and easily obtain the desired estimates. For large values, we need to exploit Hölder, Chebyshev, and Cauchy-Schwarz inequalities to obtain the desired estimates. Now let's obtain the linear asymptotics of tilde x, almost surely. Divide the formula for tilde x by t, and study the limits of each term on the right-hand side. So here on the first line, it is the expression for tilde x. Then I substitute coefficients tilde a, tilde b, and tilde c, and obtain a lot of terms. The first term, let's write, goes to 0, obviously, as t goes to infinity. One can show that the second term goes to the constant a. Indeed, a has some power asymptotic, namely constant a times x to the power alpha. F prime is for large x's is 1 divided by x to the power alpha. So one can show that indeed this term goes to a. The third term goes to 0 using the asymptotic estimates for integrals of stochastic processes. These violet terms go to 0 by the previous slide. So this goes to 0 and this goes to 0. Let's see the previous slide. So the previous slide gives some estimates, but since we have some relationship between alpha and beta, this expression 1 minus alpha minus 2 beta is positive. So as x goes to infinity, this integral goes to 0. Similarly, is for the second integral. Finally, we have the last term. This Wiener integral goes to 0 by asymptotic estimates for Wiener integrals. Thus, we obtained the following convergence almost surely. So we finished the idea of proof of the main result, which is here. As a corollary, let's apply the main result for SDEs with a Lévy noise. Let X be a solution of the following SDE, which has the drift coefficient A and the Lévy noise coefficient H. Here, Z is a compensated Lévy process with a finite second moment and with a Lévy measure nu. Let alpha be from 0 to 1 and A be positive. Let the following conditions hold. The first and the second conditions are the same as they were for the main result. The last condition estimates the squared noise H, estimates by some power function. Well, under these conditions, we obtain the desired asymptotics of the solution. On this slide, you can see the references. These are papers on results that I mentioned on the history slide. Thank you for your attention.
Okay, thank you very much. Maybe somebody have questions or comments, please.
Can you show us your the last presentation? Okay. No. Yes. Here it's very interesting. The first condition when xt converts to infinity, almost surely, is it possible to weaken this condition? To, for example, I don't know, maybe converts not almost surely, but in probability, because almost surely conversion is more restrictive. I think. Can we weaken this condition? In some case, in some sense, for example.
Well, I need to think, but I want to say that this is non-trivial condition, and it doesn't follow from the second and the third.
It depends. Yes,
Gichmann and Sikorsky developed. What do you mean?
You want to say this condition depends on the second and the third conditions, yes?
It doesn't follow from this.
It doesn't follow.
Yes. and this is important condition. Well, Gichman and Skorokhod developed methods to show such transients for solutions. For
And
SDEs
your, I'm sorry, and your solution is strong solution, yes?
yes.
Yes. Ah, okay. Okay. Thank you.
Maybe other questions, please.
I have a question. You established a result for alphas that's strictly less than 1. Could you please show the very first place where this all fails for alpha equal to 1?
Well, yes. Consider, so when alpha equals 1, an explosion may happen. So D.
No, if alpha greater
No.
than 1, the explosion may happen. If alpha,
Yeah,
If
greater
alpha
than 1,
equals to 1, it
it's
doesn't
correct.
happen.
Well, we have, well, if alpha equals 1, then I think the asymptotics is exponential, not power. So
Yes, I understand, but where does your method fail?
sorry, excuse me.
Where does your method fails?
Yeah, it fails. Yeah, it is important. So I obtain asymptotics of tilde x, and then I obtain asymptotics of x by applying well, this is f of x of t, and I apply f inverse. And I use the fact that the power functions preserve equivalence, or this power function is a regularly varying function. But exponent, or yeah, if we apply exponent, then the equivalence may fail.
I do not follow everything, because if you're written in the form. Oh, okay, I see now. Thank you.
Okay, other questions, please. I also have some questions. First of all, about this first condition, when xt goes to plus infinity. When we have usual stochastic differential equation with only linear process, there are well-known conditions from initially from Gichman-Skorokhod that give us the even sufficient and necessary conditions for this. What about the equation with Lévy noise or with jumps? Do you have something which guarantees the first condition that xt tends to plus infinity in case of equations with jumps?
Well, I have some conditions, but they may seem trivial. For example, if a coefficient is greater than some positive constant, and this noise, okay, let's even discuss the main result. And this B and C, and this B and C noise coefficients satisfy this condition with beta from 0 to 1/2, then I believe that x of t goes to
Yeah,
plus.
it's understandable, but it is it is very rough.
Well, I'm working on.
It's trivial, yeah.
Indeed, I'm working on
But
such conditions.
do you have maybe something non-trivial like like in Gichman-Skorokhod case?
Well, I'm studying this now. If we try to use the Gichman-Skorokhod technique, we obtain some integral differential equations, which is
you will have
difficult
some
to solve.
trouble due to this measure nu, yeah?
Yes.
Okay, yeah. Okay, it will be interesting. Another question is the following. you get just the first term of asymptotic. You get the statement that your solution, in case it goes to infinity and these coefficients, then your solution has the asymptotic like equivalence, yeah? But what about the difference? Because now you get this asymptotic just killing stochastic terms. Yeah, your asymptotics of the drift term is much more powerful. But the difference can satisfy some, for example, law of iterated logarithm. Yeah, next term. And here, let me mention the result of Maria Karlikova, at those time already Maria Lagunova. She proved the law of iterated logarithm asymptotic for equation with interaction. I believe that your supervisor know very well equation with interaction, and maybe it can be interesting to see what can happen, because in those cases it occurs that asymptotics is different for different omegas. We have a different constant in the law of iterated logarithm. So I think that it is the subject of your study is very perspective, and hope you will get interesting result in the future. Okay. Some other questions, please.
Maybe let me make one comment that this is the first result on asymptotics of stochastic differential equations with jumps. There were a lot of results. No, maybe not the first, the second. And this result is very non-trivial. And Viktor had to develop a lot of technique to obtain bounds for moments and for these stochastic terms. And I hope that he will be able to study multidimensional stochastic differential equations with jumps too. In this case, there will be another questions, because there are a lot of infinities, and we have to study not only absolute value of x, but probably also the angle of passing to infinity. He has the corresponding results for stochastic differential equations with Wiener noise, but for Wiener noise and jumps, it's open problem. And you see here, martingale was, so this compensated Poisson measure and this second term, so its behavior looks like, so the stochastic integral is square integrable martingale. So we used Dubs inequality, itoisometry, some Bihari inequalities, and estimated. It would be interesting to have integral without without centering. For example, if you integrate with respect to alpha stable process with alpha, say, between 0 and 1, then we may have big jumps. So now we apply martingale technique. But if we integrate with respect to Lévy alpha stable with alpha between 0 and, well, with alpha less than 2, we theoretically, we may have big jumps, and it is not clear how to work in this situation. So this will be also interesting problem for the future investigation.
Okay, so there are a lot of work.
Yes.
Yeah, okay, good. It's good news. Okay, then thank again to the speaker, and maybe Georgi know who will be the next speaker.
It will be your joint talk with King Song Wang.
Yeah. Okay, good. See you next week. Bye.
Yeah, bye.
Goodbye.
Goodbye.
Bye.
Goodbye.
Thank you.
Thank you. Bye.
Thank you. Bye.